Next, we're going to take what we just learned and extend it to define an orthogonal matrix. We're going to start by recounting the definition of an orthonormal basis, but we're going to do so in a slightly different way. The two conditions can also be written mathematically. The first, of mutual orthogonality, means that if I take any two vectors in an orthonormal basis, their inner product should be 0. Why? Because that's the definition of orthogonality. So this notation here says that as long as I is not equal to j, as long as I take two different vectors from that basis and take the inner product, I should get 0. The second condition is that if I take any vector in that set and take the inner product with itself, I should get 1. This is another way of saying that each vector is a unit vector. The trick here, of course, is realizing that when I take the inner product of a vector with itself, I'm creating the sum of squared elements. Since the norm is the square root sum of squared elements, as long as this is 1, the square root, of course, will be 1, and so the norm is 1. Now, these two facts will really help us when we consider the following example. Let's suppose the columns of a matrix are orthonormal. Here I have p vectors, v1 through vp. They are orthonormal, and I put them as columns in a matrix V. And I want to consider the matrix product V transpose V. Well, I just take this matrix, roll it on its side for the left to make V transpose, and take a copy of it on the right to be V. And in multiplying these, I can use what I know of linear algebra to realize that if V is n by p, that means that V transpose is p by n. And so V transpose V will be a square p by p matrix. Now, in order to actually do this multiplication, we're just going to take it element by element. Starting in the top left corner, I would multiply the first row by the first column to get the 1, 1 element of the product. And that would be V1 transpose V1. Moving across the row, I would then move to V1 transpose V2. And then, just to make the idea concrete, we'll go down the row. The 2, 1 element would be the V2 transpose V1. And I hope you can see the pattern here, that the diagonal elements of V transpose V will always be created by taking the inner product of the vectors with themselves. And using the fact that the columns are orthonormal, I know that all of those inner products should equal 1. So conveniently, there are 1s on the diagonal of this matrix. On the off-diagonal elements, we can use the other part of the definition, which is that when I is not equal to j, Vi transpose Vj will be 0. So I will have zeros in the off-diagonal elements. So it's a rather interesting fact that a matrix with orthonormal columns has this nice property that V transpose V is equal to the identity matrix. However, we can't say anything about V transpose unless the matrix is square. And when the matrix is square, we have a very nice property. When a square matrix has orthonormal columns, it also has orthonormal rows. And such a matrix is called an orthogonal matrix. Now, I don't know who decided to call this an orthogonal matrix rather than an orthonormal matrix. I rather wish they had called it an orthonormal matrix. It would make it easier for myself and my students to remember that. But the definition is an orthogonal matrix. It has orthonormal columns or orthonormal rows, and its inverse is equal to its transpose. So not only do we have V transpose V is equal to the identity, but we are also guaranteed that V transpose is equal to the identity. Now, if you recall from the primer material, this is the very definition of a matrix inverse, a matrix that you multiply on either side of V in order to get the identity. So the inverse of V is the transpose. It's about the easiest inverse there is to find on the planet. This also makes an orthogonal matrix easy to maneuver inside of matrix equations because the inverse is the transpose. So, for example, we can just mess around with a little algebra here. If U and V are both orthogonal, then the following equations are equivalent. Here I have x times V is equal to U times D. Now, this is an equation that you don't probably know where I came up with it at this point, and that's okay. I'm only showing you that algebraically, I can multiply both sides of this equation on the right by V transpose. And then I would have V transpose on the left, which is equal to the identity. And the identity times x is just x. So I'm left with U, D, V transpose on the right. Now, to get from the second equation to the third, I'm multiplying both sides on the left by U transpose. U transpose times U is the identity because U is orthogonal, leaving me with the third expression. And then to get from the third expression to the fourth, I just multiply both sides on the right by V. And the main point here is just to show you how easy this equation is to manipulate, because finding an inverse is as simple as taking a transpose. Now, let's try to revisit this discussion of why we want an orthonormal basis. And there are two conditions, so I think about those conditions as being two reasons. The first condition is that the basis vectors are mutually perpendicular. So they're just rotations of the elementary basis vectors. This means we can plot and consider data coordinates in a familiar way. Anything else would just be weird, non-Euclidean or affine. This is what a coordinate grid would look like if we didn't have perpendicular basis vectors. It would probably be a little odd to plot points along such a grid and try to draw conclusions. The second condition is that the basis vectors have length 1. So we want the coordinates to tell us how many units to go in each basis direction. In this way, we can focus on the coordinates alone and almost ignore the existence of basis vectors entirely. To investigate, you might consider writing this point A in the orthogonal but not orthonormal basis V1, V2, specified here. And then ask yourself, is this point, are the coordinates representing this point still meaningful to me in terms of the distance of A from the origin? And the answer you should come up with is no. Those coordinates are not still meaningful in terms of the distance of A from the origin. To summarize, a basis that is not orthonormal will distort the data. A basis that is orthonormal will merely rotate the data, meaning that all the relationships of where the points lie relative to each other will remain the same. Most dimension reduction methods create a new orthonormal basis for the data. Okay, those listed here, principal components, SVD, factor analysis, correspondence analysis, all of these methods will rely on an orthonormal basis. Here are a few practice problems just to practice some of the main ideas from this video.